Hi everyone. Today I would like to share with you the latest results from my group on energy transport characteristics of nanomaterials, and specifically for the case of mixed halide perovskites. Now I will show you how we use transient microscopy to directly visualize exciton transport in these materials and how we can conclude from these measurements that phase purity, unfortunately, may not be the holy grail that many people have been looking for. Metal halide perovskites have this by now well-known structure of a metal halide and a small cation arranged in this cubic structure of corner-sharing octahedra. In recent years, perovskites have demonstrated their high potential for lightweight, solution processable, and efficient optoelectronics. But one additional and quite unique advantage is their high tunability through changes in their composition. And of particular interest in that respect is the mixed halide cases, for instance, using iodine and bromine, where we get very wide broadband tunability of the band gap. And this is extremely valuable for the optimization of, for example, tandem solar cells or fine tuning of the color of light emitting diodes. But mixing in different halides also comes at a challenge because the soft inorganic lattice of perovskites allows for a significant ion migration, and this can lead to phase segregation. Phase segregation, in this case, leads to bandgap instabilities, where you create extended regions of low energy iodine perovskite that prevent efficient energy transport. Different strategies have been developed to prevent phase segregation, including, for example, the introduction of mixed A-side cations, doping of different elements, or reducing the dimensionality. It's tempting to believe that with these different strategies, we have resolved the issue of phase segregation, but does phase purity really mean that we have a flat energy landscape? If we look at, for instance, at the lower dimensional perovskites, right? So what we're doing in this case is we're changing the small cation for a larger cation, effectively cutting up the inorganic lattice into two-dimensional sheets. And it has been shown that indeed these two-dimensional metal halide perovskites show phase purity, so there's no phase segregation of the iodines and bromides in this lattice. But if we look at the fluorescence spectrum of these mixtures, what we observe is even though the pure iodine and the pure bromine cases are very nice narrow emission peaks, once we start mixing in, we get these broad features. These broad features, again, is not because of phase segregation, but it has instead been suggested that this is local statistical fluctuations of the iodine and bromine, meaning that not every octahedra in the system has the same ratio of iodine and bromine. Now, the real question is whether or not these local fluctuations can also affect energy transport. So to explore this, we performed transient photoluminescence microscopy of these materials. Transient photoluminescence microscopy works by basically creating a small diffraction limited carrier population by laser excitation, and we follow how this population broadens in time. Now we do this by projecting an image of the laser spot outside of the microscope and using a scanning avalanche photodiode to scan a line trace through this population, with which we record both the position and time, and can basically start mapping out how the initial narrow distribution broadens as a function of time. Please note that this is normalized, so we're not looking at the decay dynamics, we're really just focusing on how broad the distribution is. So basically how it broadens in time. This is for the pure iodine case. So you see that there's significant diffusion of charge carriers going on. In this case, they are excitons. We can quantify this a little bit better from these kind of maps by taking line traces, 0 nanoseconds and later times, and basically taking the variance of these different slices in time, comparing these and extracting a mean square displacement. So mean square displacement as a function of time gives us then this kind of plot where we see fast diffusion in the beginning and later down it slows down a little bit. Now this fast diffusion here in the beginning is linear. This is what we refer to as normal diffusion, and we can extract the diffusion constant from this initial normal diffusion. At later times, what happens is that basically traps start playing a role, but you can find a discussion about that in these more recent publications from my group. This is pure iodine, and we can extract this diffusion constant, and it's around 0.2 centimeters squared per second. Now, we can, of course, now start doing the same experiment on the different mixtures of the halides. So we have pure iodine, pure bromide, We also have the mixed case. What you can already see here of the 50-50 on this fluorescence microscopy image is this very nice homogeneous color at the center of this crystal, again indicating the phase purity of this material. So we do the measurements. We observe that both for the pure iodine and the pure bromine, there is a significant and relatively fast outward diffusion of the population. But if we look at the 50-50 case, what we observe is this complete stagnation of the diffusion. This is, of course, quite surprising, given that we have phase purity, and this would then be due purely to the local statistical fluctuations. We can do this, quantify this then in terms of diffusion constants, and we can do it for different mixtures. So what we see is this very dramatic drop over an order of magnitude decrease in diffusivity for mixing in different halides. And what we also see is a bit of an asymmetry. So mixing in a little bit of bromide into an iodine lattice apparently has less dramatic of an effect than mixing in a few iodides into a bromide lattice. It's interesting to compare this, of course, to this broadening in the emission spectra that we've seen before, where we also saw that basically in the same central region we have this broadening of the emission spectra. Now, to look at this a little bit more detail, we performed strict camera measurements, so time-resolved spectroscopy that allows us to quantify the transient redshift in these materials. And what we see is that for the low mixing ratios, we see very small transient redshifts, whereas for the larger mixing ratios, we see this quite dramatic transient redshift. So this really indicates that the local fluctuations that are then present are still causing significant energetic disorder. So we can quantify this as well by taking the difference in energy at 1 nanosecond, and we can plot all this on top of each other, where we observe now similar asymmetries in the transient redshifts as in the full half maximum of the time integrated spectrum, as in the diffusivity. We also see, of course, that transient redshift apparently is not very large at these low mixing ratios of bromide, but we already see a quite dramatic decrease in diffusivity. So can we link this a little bit better? Can we see whether or not what we are observing in the diffusivity is really local statistical fluctuations? So for this, we switch to Brownian motion simulations. And the first thing we do is we simulate what these energy landscapes look like for the different mixing ratios. Yeah? So for small amounts of bromide, large amounts of bromide to the 50-50. And we already see, of course, that the 50-50 case, due to statistical fluctuation, gives us a quite dramatic disordered energy landscape. So we take our experiment, and now we take the simulation. The simulation does not include any fit parameters. So the only thing we do is we need to take the Exciton Bohr radius of the carriers. We take for that a literature value of 0.8 nanometers, and we observe a very good match with the experiment, where we even see the similar asymmetry on the bromide side versus the iodine side. So this is for Exciton Bohr radius of 0.8. To understand this now a little bit, it basically means that if we take in a little bit of bromide, a little bit of iodide into a bromide lattice, we get small pits where excitons can get trapped. Whereas in the iodine lattice with a little bit of bromide, we just have a little bit of hills where carriers will scatter but not get completely trapped, as in this case. So this kind of explains this asymmetry that we have here. We can also extract the transient redshifts from our simulations as well. And we also see there a very similar picture, even though it doesn't drop as deep as that we see in the experiments. And this could be due to additional effects of the mixing, such as strain that is introduced that is not captured in our model. So to conclude, despite the phase purity, exciton transport is significantly affected by halide mixing in 2D perovskites. You can read a more detailed story here on this archive post that we have. To finish off, I would like to thank my collaborators at the Autonoma at Stanford and at Mississippi. And I would like to thank in particular Michael Seitz, who was the graduate student in my group who has led most of this research. Thank you very much for watching.